Let's look at some more antiderivatives. As I was saying before, we have the power rule and we have the antiderivatives of the trigonometric functions. And in conjunction with the chain rule, we can actually do a lot. We're still limited, but we can still do a lot of antiderivatives. So now if we look at the antiderivative of cosine 3x, we remind ourselves that the antiderivative of cosine is actually sine. But with this 3x here, we've got a little bit of an issue. So many students will think of it this way. They'll think of u is equal to 3x, and the differential of u is 3 dx. And so when you look here, you see that we're missing the 3. So we can always put in the 3 and then pay for the 3 with the 1/3 here, because we can move constants in and outside of the integral sign. So now when we look at this, we basically have the antiderivative of cosine, which is sine, and then of course the 1/3, which we're obliged to carry over here. So we get 1/3 sine 3x plus the arbitrary constant. Now again, when we do these antiderivatives, we take some liberties with the fact that we've got some nice conventions going on that keep us from having to write too much. So don't be bothered by the fact that it seems like we're cheating. We're really not. Okay, now let's look at the next problem. We look here and say, okay, we've got sines and cosines, and those seem to be things that we know a little bit about. Now notice here we have a power of 2 of the cosine y in the denominator. So that's really going to remind us of this green box here. That is the power rule. So what we want to do first is write it in a more user-friendly form. So let's bring the square of the cosine y upstairs, writing it this way with a negative power with the sine y dy. Now we can go back to this process here, thinking of the cosine y as the u, and its differential is just the negative sine y dy. Now when we look at the integrand, we don't have the negative, so just like we did in this problem, we can put in a negative and pay for it. So we put in the negative here for the differential and pay for it here. And now we can look at this and say, oh, we're table ready, because we basically have the green box. We have u to the negative 2 power du. So now we can add 1 divided by the new power. So when we look at this, for instance here, adding 1 to negative 2 is negative 1, as we have here, divided by the new power negative 1, and then of course the two negatives will absorb. Of course we still have the arbitrary constant, as we always do, and of course if we want to retire the negative power here, we can just write this as 1 over cosine y, and then of course from our trigonometry this is just the definition of secant y. So there's nothing gained by going from here to here, but if you would prefer to write it this way, you certainly can. Now the last integral that I have here, again, there are many ways to do antiderivatives, but at this point we want to use techniques that we understand. So even though this is a rational expression in cosine, we certainly don't want to use a more complicated substitution. So what we're going to do here, since we really don't have a sine floating around anywhere, is use the conjugate method and hope that this will help us to rewrite the integrand in a way that we can complete. So when we do the conjugate method here, multiplying and dividing by 1 minus cosine x, which is the conjugate here of 1 plus cosine x, upstairs we just get the 1 minus cosine x, and of course downstairs we have the difference of 2 squares, which gives us 1 minus cosine squared x. But that's just the fundamental identity from trigonometry, which is sine squared. So now when we look at this, we've got 1 over sine squared, which is cosecant squared, and then we have a 1 over sine times a cosine over sine, and that's cosecant x cotangent x, of course with the negative that we carry along in the problem. Now at this point we've got integrals that we actually know, but we often forget these, so we have to go back up here and recall that the derivative of the cotangent is the negative cosecant squared. So now when we anti-differentiate cosecant squared, we will get the negative cotangent. And then we remind ourselves that the derivative of cosecant is the negative cosecant cotangent. So when we anti-differentiate cosecant cotangent, we get the negative of the cosecant with the negative here. So we end up with negative cotangent x plus cosecant x plus an arbitrary constant. So again, just remember, as you're doing antiderivatives, it's probably a lot easier to go back to the corresponding derivative formulas and then just work them backwards. So for instance, if you stare at this again, you can see that the antiderivative of cosecant cotangent is the negative cosecant. But since we have another negative here, they absorb and we just get the positive. So instead of trying to memorize two sets of formulas, just remember the derivative formulas and then work them backwards using the definition of the antiderivative. And we are done.